Today, I'm going to present the cone jet and emission processes for electrospray thrusters via computational analysis. Sorry. So electrospray thruster are used in LISA Pathfinder, which is laser interferometer space antenna mission. It was flown at 2015, led by European Space Agency, and the NASA JPL also supported that project. And our team at UCLA also supported that project with the Busek company, which made a colloid microneedling thruster. The advantage of using the electrospray is it can provide the broad range of thrust to power ratio and the higher ISP, which means high efficiency for longer lifetime mission. And scalability, which can have higher thrust density for compact or smaller spacecraft, which is for in this case, we can use it for nanosat or CubeSat. The challenge of our project was three of the thrusters failed at 3,400 hours, and the LISA mission actually requires 20 times of that lifetime, which is 60,000 hours. So our objective was to make a model for the electrospray thruster to investigate the higher conductivity liquid or cone jet or droplet formation or even ion formation for live performance modeling. Electrospray thruster can be divided into two sets of applications, which is one is colloid thruster for the LISA mission. They use ionic liquid. The conductivity that we use is 1.2 Siemens per meter. And also there is a field emission electrospray thruster, which we call FEED thruster. They use liquid metal like indium, and that the conductivity itself is a 10 to the 7, which is 10 to the 6 times of that of the ionic liquid. So the LISA mission for the colloid thruster, they have higher thrust to power ratio compared to the FEED thruster, but it has lower specific impulse, which has lower efficiency. But if you can make it, like MIT is working on the arrays of electrosprays, the like nanometer size of the arrays, and that makes even more higher efficiency, higher specific impulse for the colloid thruster. So today we're going to cover the capillary, which has the higher thrust to power compared to the externally wetted, which they use for FEED or even higher ISP thrusters. So according to John Ziemers, he was our PI at NASA JPL, we discovered that the primary failure mechanism of the 3 out of 15 or so emitters was because of the overspray leading to the grid impingement. So that abnormal behavior happened when we kind of start up or shut down operating modes, and those kind of droplets hit the XL grid, and got a lot of the like shorting issues and abnormal behavior, and shut down after 3,400 hours. So we had 2 rules. Number 1 is don't hit the grids, and number 2 is don't hit the grids, according to John Ziemers at NASA JPL. So our objective was to investigate and mitigate the primary failure mechanism, in this case, the overspray. The video for the moderate high conductivity is not working, but we actually observed both low conductivity liquid and moderate to high conductivity liquid behavior. Dr. Peter Wright from our lab, he observed ethanol bulk whipping motion of cone and jet for low conductivity liquid. But when it gets to the moderate and high conductivity liquid, which we use EMIM, Dr. Nolan, he works at Navy Research Lab now. But you can see, well, not in the video, but there is a whipping motion at the end of the jet, at the end of the cycle, at end of the pulsating cycle. So that means there are high charge density, concentrated at the cone to jet region. So we're going to model not only for the low conductivity liquid, but also moderate to high conductivity liquid. But the challenge is there is no model for moderate to high conductivity in the community. So I briefly went over the introduction, motivation, and I will go through a slide of theory and our results for axisymmetric and asymmetric tilted cone jet emission, and future research also the thing we do at Air Force Research Lab. The physics is quite simple. It's electrohydrodynamics. We use two sets of equations, which is hydrodynamics and electrostatics. So we casually solve Navier-Stokes equations, and we kind of solve electrostatic force and surface tension force as a source term and put it into the Navier-Stokes equation. And we use volume of fluid method for the transport of the liquid, and we calculate the volume fraction for each of the cell size iteratively for each time step. Electrostatics, we solve Gauss's law and charge conservation to get the charge density and electric field to get the electrostatic force, and we put that into the Navier-Stokes equation to get iteratively to get the balance of the normal direction or tangential direction of the electrostatic forces, gravitational force, viscous surface tension, and polarization force in this case, to get the meniscus and the droplet breakup, which we're aiming for. The key thing for the model we built is that it can capture the unsteady physics that is required for our mission, because it all happens at the startup or shutdown condition, for the failures. So we need that unsteady model to capture that. We can capture the satellite droplet and even the recirculation flow inside the meniscus. So as the time goes in the startup conditions, you can see that the recirculation flow is growing and dominating inside the conical meniscus. And also you can see the voltage sensitivity. When you apply higher voltage, you can see steeper meniscus and changing into a smaller jet size and smaller droplet and higher charge to mass ratio of the droplets that can have the higher thrust power. So this is the discretization of electrospray thruster model. I was in charge of the emission model, which breaks up the ionic liquid into a cone jet and droplet breakup. So unlike the particle models, fluid flow models are a continuum approach, numerical approach, and it is multi-physics and multi-scale, where the emitter size is 60 microns, but jet diameter or the droplet diameter is 10 or 100 nanometer size. So it is a challenge to resolve that the multi-scale problem. So we were able to get the 2D axisymmetric EHD computational fluid dynamics model. These are our modeling team. Dr. Uchizono, he works at Navy Research Lab. Dr. Kenna, she's working as postdoc in Cornell. So we had a fantastic team back in the lab. We looked into several non-dimensional parameters like electric bond number, charge relaxation time to resolve the time, and relative permittivity, capillary number, or non-dimensional flow rate, or electric Reynolds number. So we look into these kind of non-dimensional parameters to balance these kind of forces acting at the meniscus. So we'll go through, I will not go into the details, but these are the key parameters that we use. The challenge of getting a higher conductivity model is that we used to have the spurious current because of the numerical diffusion. So the original model used the weighted arithmetic averaging method to determine the electrical conductivity based on the cell size. But this kind of arithmetic averaging is slowly transitioning across the interface. So that means you get a lot of the charge density leaking outside of the interface of the liquid and gas. So also this gets even worse when we use higher conductivity, because large number of calculation iterations, because of the small step size, we get a lot of the charge leaking by using the weighted arithmetic averaging. So in that case, we devise a new way of capturing interface capturing parameter f. In that case, compared to the weighted arithmetic averaging, when we use 20 of the f value, then you can see the steeper cone jet, and you can actually conserve the charge inside the meniscus, and also the droplet, where you get finer jet, a smaller droplet, and steeper meniscus because of the higher electrostatic forces. And we validated against the experiments as well to start at the bottom line. So we were able to get the low conductivity simulations compared with Kakutang and Gomez in 1996. And it was pretty looking good compared to the results. And also we were able to validate some of the diameter results or even scaling equations and changing the voltage or electric Reynolds number or even different flow rates. So that was a starting point. And then we moved into moderate conductivity simulation using tributyl phosphate. In this case, conductivity was like 1,000 times of that of the low conductivity liquid. And results also agreed well with experiments and scaling equations by using the parameter F. And this is kind of like a fun topic in our lab. Dr. Peter Wright, he actually came up with the idea of coaxial emitter, which is we can introduce the needle inside the emitter. And that allowed us to have the higher charge density at the tip of the needle, and it applies more electrostatic force and have a better performance using the coaxial emitter. So we modeled that coaxial emitter and we patented, and a lot of the people in the community really liked this idea. And also we did a lot of the sensitivity studies. In this case, we did varying temperature sensitivity studies because density, electric conductivity, viscosity, surface tension is changing as a function of temperature. The operating condition or operating temperature is from 280 Kelvin to 360 Kelvin. And even in that small range, we can see from the model that the performance is very different from the 280 Kelvin. And to analyze that, we kind of implemented the energy equation to our two sets of governing equations. In this case, we also put the self-subsisting electrical conductivity depends on temperature or density, permittivity, surface tension, and viscosity. Also, what we did for the electrical conductivity, we also put the same technique. We devised parameter F to the thermal conductivity kappa, and that allowed us to conserve the temperature or conserve the energy in this case of the modeling. So we were able to get the meaningful results that the Joule heating is happening at the cone to jet region, and that applies more crazy whipping emission inside the jet and the tip of the cone. Also, higher conductivity simulation, we were able to match the results from the journal paper. The key thing that we noticed from the model is that we were able to see additional recirculation cell at the tip of the meniscus. So this is not a steady state. This is a transient, the end of the pulsating cycle capturing model result. So that means like this upper, if you see the upper figure at the upper right side, this is the low conductivity simulation. And you can see there's only one set of recirculation cell for the heptane for this case. But when it gets to the higher conductivity, there are additional recirculation cells. Also, when you decrease the non-dimensional flow rate, in this case, it's a flow rate. And electric Reynolds number, if you increase that, for example, if you increase the conductivity, or when you increase the voltage, then you get several other recirculation cell within the meniscus. And that means from the other journal articles, this is the ethanol result. I'm sorry. This is the ethanol results where the recirculation flow has an unbalance even in the ethanol results. And in our model, we built a 3D model to capture that unbalance of the recirculation cell. And then we cut into a plane and discovered that the recirculation flow causes two opposite directions of the toroidal flow. And it becomes to the toroidal flow. And as we capture at the end of the pulsating cycle, we get the whipping emission at the end of the cycle. And we knew that this kind of unidirectional toroidal motion is the reason why we have the whipping emotion that affects the hitting the grid that we have to, to not happen in our thrust mission. So in short, the recirculation unbalance leads to the toroidal motion, and we have to avoid that to be happening. So again, don't hit the grids, but we have to avoid the unbalance of the recirculation cell. Also, we studied asymmetric cone tilt. As we increased the electric potential, we were seeing steady state tilted jet, and even further, we get the multi-jet mode. And also, we did ethanol experiments that we observed steady state tilted cone emission at the electric bond number at 30. And we wanted to know why this is happening. So we modeled a three-dimensional EHD model to capture that cone tilting emission using 20% ethanol and 80% terpenol. It is a very high surface tension coefficient liquid. And as we increase the voltage, then we were able to see the charge density is concentrating at the concave meniscus at the left side of the meniscus. And that leads to the higher tangential electrostatic force, and that is balancing with the higher surface tension of the left side of the meniscus. So that's why we're having a steady state tilted cone jet emission. That's what we discovered from the model. And this is a transient evolution of tilted cone jet emission and a lot of the data analysis. So I'm sure it's the time. So in conclusion, we newly devised interface interpolation scheme for the volume of fluid method, and we were able to reproduce from our journal articles and meniscus in the cone to jet region. Also at FRL in space propulsion branch, we mostly focus on electric propulsion, plasma propulsion, chemical propulsion, and monopropellant and molecular propellant and data analysis, like the digital twin environment that we can't, experiment all the time because the xenon gas is very expensive. Also, I'm working on the Bayesian Markov chain Monte Carlo fitting for the krypton. This is the gas that the SpaceX Starlink is using at the moment. Because xenon gas is very expensive, although the performance is very low, we're trying to use the krypton and have that kind of data fitting. We're working with John Eam at NASA Glenn, and I'm sure he's also Korean. So if I have the chance, I might introduce him our community. And also we're also working on the monopropellant chemical reaction inside the thruster as well. So we're doing a lot of cool research. We're open to any collaborations. So if you're interested, please don't hesitate to reach out to me. And thank you for listening, and thank you for setting up all the meetings today. Thank you.